Grade 12 Physics, Energy and Momentum, Note number 6. Conservation of momentum in one dimension. So just like conservation of energy, we can treat momentum in a similar method, knowing that the total momentum in any collision is conserved. If we find the total momentum before a collision, that's going to be equal to the total momentum after a collision. So we can write that out in words here. Even if we have multiple objects, the sum of all that momentum initially equals the sum of all the momentum finally. So here we can say P equals P prime, where the prime denotes the final state. Even if we're dealing with two objects, that total momentum initially is going to be P1 plus P2 equals P1 prime plus P2 prime. And knowing that momentum is made of mv, we can also expand it like so. We're going to be dealing with three types of collisions whenever we're talking about momentum. The first one is called an inelastic collision. That's basically where we have two objects colliding and then they stick together after the collision. So that's in that drawing right there. The next one will be an elastic collision, where we have two objects colliding but they don't stick together, they just bounce off one another. The final one is an explosion, which is basically opposite of an inelastic. We have two objects that start together, they explode apart, and then they're separate afterwards. Let's move into an example here for a one-dimensional collision. Let's do an inelastic problem. Let's say a truck, which is moving up to a stoplight, can't slow down enough, or actually doesn't slow down at all, hits a car that's sitting at that stoplight, and they stick together for an inelastic collision. The truck has a mass of 578 kilograms. The rest of the information will be given here in the diagram. So there's the truck moving forward at 9.2 meters per second with its mass. The car is sitting there at rest, has a mass of 328 kilograms. Afterwards, they stick together and move forward at some unknown velocity that we're going to solve for. So here, P equals P prime. So that's the momentum of the truck plus the momentum of the car initially equals the momentum of the car plus the momentum of the truck afterwards. This car is at rest to begin with, so this term, because the velocity is 0, is going to go away. Afterwards, when they're stuck together, the velocity of the car and the velocity of the truck are going to be the same because they're basically one object. So we're just going to call both of those terms V prime, and we can factor it out of both of those masses. Now let's solve for the V prime. We rearrange our equation, put in our numbers, and we find that it has a final velocity of 5.87 meters per second. This should be less than the initial velocity of the truck, and if we look up above, it is. It's less than 9.2. Our next example here is going to be an elastic collision. Let's say we use baseball as an example. A ball is being pitched towards a batter. The bat is moving forward to hit that ball, and then we'll have an elastic collision where the ball will be hit out into the outfield. Let's say a bat hits a baseball like so. What would be the final velocity of that baseball? So beforehand, we have the ball moving to the left, 0.2 kilograms at 40 meters per second. It's going to strike the bat, which is moving forward, 35 meters per second, and has a mass of 0.85 kilograms. Afterwards, that ball is going to be moving forward. That's what we're going to calculate. We're going to try and figure out its velocity. But that batter's going to swing through. The bat's going to be going a little bit slower. It's going to be going at 16.5 meters per second. We need to define everything pointing to the left is going to be positive, and everything pointing to the right is going to be negative. So here we go. Momentum initially equals momentum finally. Let's call the baseball as object number 1 and the bat as object number 2. So putting in our numbers, that baseball initially is moving in the negative direction, so we need to put a negative 40 for that velocity. We put in the rest of them, solving for that V1 prime, because that's the final velocity of the baseball. When it's all said and done, V1 prime equals 38.6 meters per second. It's a positive value for velocity, meaning it's going in the correct direction. Example 3, it's an explosion. Let's say, so we just need two things that are separating. Let's say there's an astronaut floating in space. It has a wrench in her hand. She's going to throw the wrench in a certain direction, which means she's going to go opposite of that. So we're going to try and calculate the astronaut's final velocity. Before that explosion, they're together, just floating at rest. So here's our astronaut holding onto a wrench. The astronaut's going to be 50 kilograms. Wrench would be 2.4 kilograms. So the wrench is now thrown. Let's say that's sort of the center of our diagram here. So the astronaut has now moved over a little bit with some velocity, and the wrench, which is going to be going faster because it's lighter than the astronaut, is going to be moving away in the opposite direction, 9.2 meters per second. Let's calculate the velocity of this astronaut. Again, everything to the left is positive, everything to the right would be negative. So here, momentum of the astronaut plus momentum of the wrench equals the final momentum of the astronaut plus the final momentum of the wrench. Initially, both of them are at rest, so both of those first terms are going to go to 0. We're going to rearrange to start to solve for the velocity of that astronaut, making sure we have the proper negatives in there. For negative direction, we find the final velocity of the astronaut is 0.44 meters per second.